Hello, everyone. We are going to consider today integral test and how this test is applied or how we applied integrals to some estimations. So we are going to start with considering a series, which is a very simple so-called p-series. Okay. And P here is going to be equal to, so my series is going to look like this, 1 over n squared. And we'll go from 1 to infinity. P series with P equals 2. So how are going to be the terms of this series? Okay. So we have 1 over 1 square, 1 over 2 square, plus 1 over 3 square, plus and some other terms up to infinity, right? What I'm going to do, guys, I'm going to graph a function which is similar to this series, just going to be 1 over x squared. What is the difference between series and this function? Series is going to take only natural numbers as n, 1, 2, 3, and so on. Function is going to just accept any real numbers. So it can be 1.5 or 3.14, something like this. I'm going to graph this function and use it to estimate the sum. So this function is 1 over x squared. 1 over x squared is going to look very much like 1 over x, just a little bit kind of lower. I'm going to label my 1 first, okay? I need kind of higher one. So my 1 is going to be here. And in this direction, 1 is going to be here. 2, 3, 4, 5. Here is x, and here is going to be y. Well, because my numbers are going to decrease rapidly, I want to see them a little bit like, so when x equals 1, it's going to go through 0.11, right? When x equals 2, it's going to be already 1 over 4, somewhere here. And I'm going to approximately graph the curve. The curve is going to look like this, right? So that's a curve. Now, guys, what I'm going to do, guys, I'm going to pick up some points at intersection of number 3, number 4, and number 5 was my curve. And I'm going to build rectangles. I'm going to base the height of these rectangles on a function. Please watch how I build my rectangles. So that's going to be my first rectangle. And over here, guys, going to be my second rectangle, my third rectangle. You see the rectangles are becoming smaller, smaller, and smaller. So the height of each rectangle is equal value of a function at a certain point. Let's calculate area of these rectangles. What is area of one rectangle? I'm going to consider this one. For example, what is going to be the area of this rectangle? Well, we know that the area of the rectangle is going to be the width over height. And in our case, height is going to be what? The value of a function at this point, which is going to be 1 over 2 squared. And the width of the rectangle is going to be 1 unit exactly, right? All these rectangles are going to have a similar area. I'm going to label it area number 2. For example, area number 3 is going to be 1 over 3 squared multiplied by 1. Each rectangle is going to have the same width. So if I want to calculate all these rectangle areas, what I'm going to have? Well, let's write it down. So the net area of all these rectangles, area is going to be 1 over 1 square by 1 plus 1 over 2 square by 1 plus 1 over 3 square by 1. And kind of all of them are going to be multiplied by 1, which are going to produce just my series, right? 1 over 1 square plus 1 over 2 square plus 1 over 3 square and so on. So basically, Area of all these rectangles is nothing else than the sum of my series. What I'm going to do, guys, I'm going to separate the first term of my series and just write down this term as 1. And I'm going to now shade the area under the curve over here, starting 1. Do you see that this area is greater than like under rectangles? So all these terms are going to be less than what? Than area under the curve, which is 1 over x squared dx, right? And the starting point is 1, and ending point is going to be infinity, right? Which is going to give us improper integral. So I'm going to do this. I'm going to write down plus integral from 1 to infinity, 1 over x squared dx. And here, guys, instead of equal sign, I'm going to put actually exactly less, right? Because we see that obviously integral is greater than rectangles, and it's like everywhere function under the integral is greater than rectangle. Something happened to my pen. Let me make sure. Oh, just too slow. Made so many inequalities. Wow. What I can do, guys, over here, I can actually calculate this integral. It's a proper integral, not too difficult to calculate. Let's calculate it. I'm going to copy 1, and the integral is going to be negative 1 over x, right? If you differentiate it, you are going to get negative, you're going to get positive 1 over x squared. Substitution 1 and t, and here is a limit as t approaches infinity. Improper integral, right? Which we covered at the end of chapter 7. Oh, let's do the substitution. That's 1. And I'll substitute the upper limit minus 1 over t plus 1 over 1. What is going to be the limit when t goes to infinity? Limit of this term will go to 0. And I'm going to get just 2. So that's going to be upper limit of my sum. So I can actually tell that my sum is less than 2. Wow, can it go to infinity? Well, kind of obvious that because the sum is less than 2, it will not go to infinity. It's going to be limited by 2. And partial sums of this sum are going to be like, remember the theorem somewhere about the sequences where we have a limit of monotonic, just the theorem was a theorem about limit of monotonic sequence, right? The monotonic bounded sequence is going to have a limit. Just what kind of sequence we are going to consider? Let's consider sequence of first partial sum. Maybe I should consider it over here. So this is my first partial sum S1, my second partial sum is S2, and my third partial sum is S3. So what we can write down about this? We can write down that's S1, S2, S3. That's a sequence of partial sums, right? We know that the series has a limit when this sequence has a limit. So actually limit of Sn as n approaches infinity is equal to the sum of series, right? But this sequence is going to be bounded. I'm going to write it down, bounded. How do we know it's bounded? Well, it's obviously that the sequence is greater than 0 because all terms are positive and squared, right? I'm going to put our sigma over here. And also, it's less than 2. We just already calculated this. So, bounded and then monotonic. How do we know it's monotonic? Well, if you consider each sum is going to add a little bit more, right? So, sum number 1 is, maybe I'll write it down somewhere because maybe it's not very clear. So sum number one is 1 over 1 square, right? Sum number 2 is 1 over 1 square plus 1 over 2 square. Sum number 3 is 1 over 1 square plus 1 over 2 square plus 1 over 3 square, and so on. You see that each sum is greater than the previous because we are adding a little bit to each sum. So we can write down that it's monotonic. So S1 is less than S2, is less than S3. It's actually monotonically increasing. Monotonically increasing. So we know that if the sequence is bounded and monotonically increasing, it's going to have a limit, and that means that the sum is going to have some limit S, which means that that's going to be like convergent sum. Convergent. They're going to say that the series is convergent. Now, it looks like no matter what kind of function we have here, we can always make the integral and make the same building, right? Not actually true. I'm going to consider the next example. So that was example 1. Let's consider now example 2. Let's consider series 1 over n. This is p series with p equals 1, right? And from 1 to infinity. So if I write it down, I'm going to have this series 1 over n, and from 1 to infinity, and the terms are 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, and so on, right? Very good. I'm going to apply the same technique over here. I'm going to build a function. Let's imagine that 1 is somewhere here, and this is 1 over x, similar to my series, right? And let's imagine this 1, this is 2, this is 3, 4, 5. 1, 2, 3, 4, 5. So guys, now guys, what I'm going to do, instead of building my rectangles backwards, I'm going to build my rectangles forward. We are not going to get different rectangles because we build them forward. If you build the rectangles backward, that's still going to be same bunch of rectangles because the height of the rectangle depends on the value of a point here, right? And the height is going to be same no matter whether you build it forward or backward. Well, similar to previous consideration, the area of rectangles is going to be what? 1 over 1 multiplied by 1 plus 1 over 2. The height over here 1 over 2, and the height over here is 1 over 3, and the height over here is 1 over 4 by 1 plus 1 over 3 by 1 plus 1 over 4 by 1, and so on. So basically, if you kind of forget about this multiplication by 1, that's the sum of my series, right? Now, guys, if you consider the integral underneath of these rectangles, you see this one. What you can tell about this integral? It's obvious that the integral or area under the function from 1 to infinity, 1 over x dx is less than rectangles because all rectangles are higher than the pieces of function or area under the function, right? But if we calculate this integral, we're going to find that it's a limit. 1 over x is going to give us a ln of x, right? Substitution of 1 in t goes to infinity, and we know that logarithm at infinity, this one goes to infinity. So this equals to infinity. Means that my sum over here, which is my area actually, is going to be greater than infinity. Well, if sum is greater than infinity, it's obviously that it's not going to be convergent. It's going to be divergent. Divergent. Now the question is, well, does it mean that I kind of, the result actually depends on the way how I build my rectangles. Here I build my rectangles backwards and everything is convergent. Here I build my rectangles forward, here, and it's kind of divergent. Means that I can prove that this one is divergent. Oh, guys. Actually, if I build in the case of example 2, my rectangles backward, I'm going to just figure out that my sum is less than infinity because we are going to have same integral plus one, this one initial rectangle, and that's going to be like all rectangles are going to be less. But when the sum of something, when the sum is less than infinity, it's actually can be anything, right? You understand that actually something less than infinity can be a number, for example, 100, also can be another infinity, just smaller. Infinity over 2 is still infinity. You see? That's why I was building my rectangles forward, because actually my integral here, I show it, my integral here was divergent. And because I knew that integral is going to be divergent, I build my rectangles above that integral. And I see that the sum is divergent too. And here in example number one, I've seen that my integral is convergent and I was building rectangles opposite direction. So basically, no one is really building rectangles. People just compare. Okay, is the integral of a similar function to my series convergent or divergent? If it's convergent, then the series, you can always build rectangles backward and it's going to be convergent. If it's like divergent, you can always build rectangles forward and show that it's divergent. Interesting theorem, right? We can summarize this theorem into so-called integral test. Let me write it down. Integral test. So integral test is going to have some restrictions on function, right? My function f, which I produced for my series, is supposed to be continuous, positive, and decreasing on interval from 1 to infinity. Then number one, if integral from 1 to infinity f of x dx is convergent, then the series of an is convergent to. I'm going to write down that an equals f of n. That's a connection between the terms of a sequence and the function, right? If integral from 1 to infinity f of x dx is divergent, then the series an and from 1 to infinity is divergent to. So kind of strange theorem, which works only one direction. One direction means that you check the integral and then the series is going to do the same as integral or behave same way. Again, why? Because we always can build rectangles, whichever direction we like. And if integral is divergent, we are going to build them above. And if an integral is convergent, we are going to build them below or backward. And this way, we are going to show that either the sum is less than a number or a sum is greater than infinity. Why do we need this continuous, positive, and decreasing? You probably see that, like, if the function is not decreasing, it's going to mean that we're going to violate the divergence test. Remember, we had divergence test, which tells if limit of a term does not go to zero, the series is divergent. If the function is not decreasing, the series is going to be divergent. Just because if not decreasing, it doesn't go to zero, and that's it. Okay. So now we will try to apply this test to series just to do a little bit of practice. Okay. And by the way, guys, the second example we considered, but besides it's a P series with P equals 1, also has a special name, and it's harmonic series. Remember, in the previous section, I told that harmonic series is divergent, and I did not prove it. Actually, that's a proof that harmonic series is divergent. Okay, I'm going to consider two series. with two different p's just to kind of make it more easy to calculate. So example, series 1 over square root of n, and from 1 to infinity, and the series n from 1 to infinity, 1 over n cubed. So there are two series, and I'm going to check if they're convergent or divergent. I'm going to start with the first one. So the idea is to calculate the integral. And integral is going to be 1 over square root of x dx, right? If we integrate the square root, we are going to get what? Well, what we differentiate to get 1 over square root of x. Maybe I'm going to write it down like first. X to the power of minus 1 over 2, right? To make integration a bit easier. X to the negative 1 over 2 dx. And I'm going to now put a limit. Integral of this is x plus 1 is 1 over 2 and over 1 over 2, right? And t goes to infinity. Remember, that's improper integral, and the limits are from 1 to t. I'm going to have a limit. So here I'm going to have a square root of t. This 1 over 2 is becoming like 2 over here minus 2 square root of 1. T goes to infinity. Well, we see that obviously when t goes to infinity, this term goes to infinity and it's divergent. So by integral test, the series, yeah, no, lots of handwriting, right, is divergent too. Well, for the second one, the integral from 1 to infinity 1 over x cubed dx is going to be equal limit. Let's just integrate it. It's going to be 1 over, that's integral. And guys, if it's too fast for you, you can just stop the video at this point and try to calculate this integral. I don't want to waste too much time on like basic integrals. It's the same power function, just the negative 3 plus 1 is negative 2, and divided by this negative 2. So if I substitute t, I'm going to get negative 1 over 2t squared plus 1 over 2, substituting 1. And when t goes to infinity, this will go to 0. And I'm going to get 1 over 1, convergent. So I'm going to kind of consider the same sentence. By integral test, the series is convergent to. Well, maybe I should write down which series convergent. See? So that's how we use integral test. Guys, now we are going to create a separate test, which is called the p-series test. Because for p-series, this integral test works not only for p-series, it works for any series for which you can actually do the integral. But for p-series, we know the answer, right? For p-series, we can integrate it in general. Let's do it and kind of make a general conclusion about p-series. So imagine that we're going to consider p-series. And p-series are looking like 1 over n to the power of p. We are going to start with p. We're going to consider three cases. P less than 0, p equals 0, and p greater than 0, less than 1, p equals 1, and p greater than 1. Well, just like to see like all possibilities for p. Well, what is going to happen when p is less than 0? Basically, p is negative, like minus 1. Well, 1 over n to the negative 1, it's actually just n, right? So when p is less than 0, we have negative power here, which is going to mean that it's going to be actually the series of n to the power of negative p, where it's a positive power. When n goes to infinity, the term will not go to 0. Term goes to infinity. We're going to use here divergence test. An, sorry, my pen is not. An goes to infinity, not equal to 0. Remember. What is going to happen when p is equal to 0? You're going to have a bunch of ones, and if we have infinitely many ones, we're going to have series of ones, which we have 1 plus 1 plus 1. If you have infinitely many ones, we're going to have infinity. So divergent to divergent. So what is going to happen between 0 and 1? When we were doing improper integrals, we have seen that we are going to have, I'm going to consider this one. We are going to have the integral of 1 over x to the power of p dx is going to be actually equal to what? Limit of x to the power of negative p plus 1 over here, negative p plus 1, right? Substitution of 1 and t goes to infinity. Just do it one more time. It's going to be a limit t to the power of negative p plus 1, negative p plus 1, minus, actually plus 1 over, minus actually, let's do minus. Minus p plus 1. I don't want to change denominator, okay? So t goes to infinity. Well, what happens to this term when t goes to infinity? Well, it depends on the power, right? Our power is from 0 to 1. From 0 to 1 means that I'm going to write on 1, thus from 0 to 1, right? If I put minus in front of p, I'm going to have minus 1 minus p less than 0. I'm changing the sign of inequality if I put minus in front. Now plus 1 on both sides. So plus 1 here, plus 1 here, and plus 1 here. 0 plus 1 minus plus 1 and 1. So when p goes from 1 to 0, the power goes from 0 to 1. Means that this power of t is actually something like 0.5 or something like that. Like case we had with a square root. This p is from 0 to 1, right? It's 1/2. And our integral was divergent because actually after you integrate it, it's jumping up and becoming a number going to infinity. So positive power is going to give us divergent integral. Okay? When p equals 1, when p equals 1, we have integral 1 over x dx. We do know that integral is divergent. And we call this a special harmonic series. And when p is less than 1, what are we going to have? The very same integral is going to be like, we're going to have term t to the power of minus p plus 1 over minus p plus 1. But if p is less than 1, then minus p is greater than minus 1. We're changing the sign of inequality. And plus 1 minus p plus 1 is greater than 0. So the power is going to be, how come it's greater? I think I changed here something. I think what I did, when I was copying this inequality, I placed a sign opposite direction. It's supposed to be greater than 1. And the sign over here is less than, and the sign over here is less. I know what's supposed to be the answer. So you see that the power minus p plus 1 is less than 0, means that this t will sit in denominator. When it goes to infinity, it's going to be divided by infinity. And this is going to give us convergent integral. So we are going to have actually, this one is going to be less than 0. Power is less than 0 means that it's going to be 1 over minus p plus 1, the coefficient. And here, t to the power of p minus 1. That's going to be something positive, and that will go to, whole thing will go to 0 when t goes to infinity. Okay, maybe not very clear from. Well, dry conclusion to us. When we have p series, when p is less than 0, equals to 0, or from 1 to 0, or even equals to 1, all these cases are divergent. By some other case, like this is divergence test, this is divergent because bunch of ones, this is divergent because integral is divergent, this is still divergent integral, it's just not the power function integral, but it's still divergent. So all this divergent. The only convergent case for p series, so p series convergent only for p greater than 1, which means that if you have 1 over x squared, 1 over x cubed, 1 over x to the power of 5, like 1 over x squared, 1 over x cubed, or 1 over x to the power of 1.5, anything greater than 1 will give you convergent integral. Okay, when I was giving you the theorem, I forgot that actually this relation works in both directions. Sometimes you know the sum of series, and you are going to conclude that the integral is convergent. The idea is that they both converge at the same time, series and integral. We are going to mostly use it like integral, calculate the integral, and kind of convince that it makes a series conversion, but actually it can be opposite direction. Okay. So that's how we deal with the series. I'm going to consider another example just to show you how everything works when your series is not P series. Not P series. Sum of series, which is going to look like n, ln of n, going to start with n equals 2. Why? Because we cannot divide by 0 and ln of 1 is equal to 0. So let's consider integral from 2 to infinity. 1 over x, ln of x. I think here we do see obvious substitution. U equals ln of x, right? Because this is a derivative. Du equals 1 over x dx. That's pure derivative, and we are going to have 1 over ln of x d ln of x, kind of my new variable. And what is going to be? Going to be a limit as t approaches infinity. And here, 1 over x, if you consider this as u, that's 1 over x dx. 1 over x dx, it's ln, right? Again, we are going to have two ln's, ln of x. I'm going to put absolute value here. And the substitution is going to be from 2 to t. And guys, ln of ln, like if x goes to infinity, then ln will go to infinity, and then ln of ln will go to infinity too. So it equals to infinity. And we are going to have divergent series. Divergent. Guys, because we are going to have so many tests about the series, you will need to label the test. So by integral test, make clear statement about which test did you use. Okay, of course, there are many more series which we can test using integral test, but let's now talk a little bit about like, okay, now, why do we need to know that the series is convergent? Because it does not give us the sum of series. Normally, what we care is the sum of series. So knowledge that the series is convergent just tells us that it's going to be some number, but it's not going to give us a number itself. So for the number itself, we're supposed to do some extra work. That's what we are going to do in the second part of this section. I think I'm going to finish this video at this point, and the second part is going to be a separate video. Otherwise, this video is going to be too long.